now get the recording started. A few things while we're waiting for other people to join. Have finished almost all the grading in the exam, and I'll try to get everything cleaned up and the final number corrected, and then input to the system by Thursday afternoon, so we can see each other and discuss about it. I'm not so bad. How to say that? I'm not feeling so bad about it. I think the average is pretty good, around 80s, and I think a lot of students has good turnout. But I do spot some problems as well during the exam. Okay, just shows that some of the details were instructed, but I don't think were implemented very well. So I'd like to have a discussion with you guys on Thursday how to improve our understanding of these few things and go through the exam with you. All right, and since we'll be seeing each other on Thursday, most likely what I'll do is that I'll bring the exam paper with me on the PDF, to my office. And then after talking about exams, maybe you can stop by my office and take a look at your exam if you want to, and we can go over some of the problems if you feel like something was still muddy. Okay. All right. So without further ado, let's continue our course. And our course today, starting at shear design for reinforced concrete structures. Right. So first of all, let's take a look at the shear design. Right. So we talked about last week. What is concrete shear? Right. So there are two components of the shear in concrete, right? So last time we talked about the total shear resistance can be divided into two parts. That is the contribution from concrete, VC, and contribution from the steel, which is the reinforcement VS here, right? So for the concrete contribution VC, how do we calculate that? We use an empirical equation, right? Empirical equation. And this is equation right here, empirical equation, okay? By the way, empirical equation means that you do the equation by fitting, right? It's a experiment, it's a data fitting process, right? It's an empirical approach. So the equation equal to VC, which is a shear resistance in concrete, equal to 2 lambda. Lambda is a lightweight indicator. For lightweight concrete, 0.75. For normal weight concrete, 1.0. And square root of F prime C being the compressive strength of the concrete, BW, which is the width of the section. And mind you that this width is the narrowest width of the section, okay? Narrowest. That means that if I have a T section, that's the width of the web, rectangular section, width of rectangular, and box section, width of the webs, right? So it's always the narrowest section of the narrowest width of the section, okay? And then multiply ds, which ds is the depth of the beam, all right? So that being said, once we have the concrete contribution, we can then calculate the reinforcement contribution of VS equal to AVFYT ds divided by S, right? So AV is the cross-section area of the stirrups. That is the transverse reinforcement, area of a transverse reinforcement, okay? And that is the cross-section area of transverse reinforcement. And know that we have usually two legs of a stirrups. So that means if you have two legs, each leg have a 0.11 inch square for number 3 stirrups, you end up having a 0.22 inch of square area for the stirrups, AV here, all right? And now the tension force per each stirrups give you a VFYT, where FYT is the yield strength of the stirrups, all right? So that is one stirrups contribution towards shear. And you want to calculate how much total contribution you have from the stirrups. You use AVFYT multiply ds over S. Right, ds over s. How ds over s come from? Right, so you can see from this diagram on the left right here. So we have a crack of ds, right, and that ds is equal to the depth of the section because we assume it's a 45-degree of a diagonal crack. 45-degree of a diagonal crack. So tangent 45 equal to 1, right? So ds over ds equal to 1, right? So with that, we can calculate the number of stirrups across the section. Number of stirrups across the section have to be ds over s, okay? Now, while we're at it, right? I want to add one small feature here, and we will talk about this again later in lecture, but I thought that since we're here, so knowing this, right? Knowing this, I know that I need to have so many stirrups across the section, right? And ACI says that you need to at least have one stirrups, okay, in the cross section, okay? This is very important. You need at least one stirrup in the cross section. That means that your spacing requirement for the stirrups, S, right? So ds over s has to be greater than 1, right? So that means that you need actually one stirrups, okay? And apologize, I think I made a mistake here, should be actually +1, right? There's a 1 additional spacing, right? So actually this is 2, right? So matter of fact, you are actually needing a s over, sorry, has to be smaller than or equal to s ds over 2. ds over 2. Okay, that means that at least I need to have one stirrups, right? So imagine this is the middle distance, midway, and that is the one stirrups you need in the cross section. Okay, and we will talk about this, right? We'll talk about this, but at this point, you start to realize that the spacing of the stirrups, how much away you put the stirrups away, dictates how strong the shear resistance of the stirrups, okay? All right, so that pretty much tell you how much of a contribution for the stirrups, but keep in mind that this is for vertical stirrups. That means that the stirrups are vertically aligned. When I say vertical, it is like this, right? Vertically aligned. But if I have stirrups, that is in the angle, right? That is in angle. So say that, well, let me just remove this. You don't have to confuse yourself. So say that I have a vertical stirrups are inclined. Vertical stirrups now inclined. That means that I have my 45-degree crack right here, and I say that the stirrups were in the direction of this crack like this. Okay, so the stirrups were inclined in the angle with respect to the directions like this. All right, and now let's just say that if I extend this line here and the angle right here is alpha, right? Then they're the same angle anyway, right? So they're all alpha. Okay, they're inclined by an angle of alpha in respective to the horizontal line, right? To the reference horizontal line, right? So let's just connect them together so don't confuse yourself. And this is what it is, right? This is the angle alpha right here, Okay, let me just connect them together, okay? So if this is the case, right? And the shear resistance is the purple color back again, Vs. And mind you that this is inclined, okay, not vertical anymore, inclined, have to equal to AVFYT. Again, that's the shear contribution from each stirrups multiply distance ds, depth over spacing s, and then multiply angle related function out, and that is sine alpha plus a cosine alpha. All right, so that is the inclined stirrups. So you added this term at the end of it to represent the effect, of the inclined stirrups. Okay, all right. Okay, so that is how much contribution you have from the stirrups, from the reinforcement. All right, so now at this point, right, I can start writing the formula for shear. So shear design, right, has to follow this formula down here. So shear design equations, right? Shear design equations. And let's take a look at them, right? What are the shear design equations? So VC is actually the red color. So you will remember this, right? So VC is the contribution from concrete, and that has to equal to 2 lambda square root F prime C BW ds. All right. And VS, which is the shear contribution from the stirrups, have two possible terms, right? A VFYT and ds over S. And this is for vertical stirrups. Okay. And then AV FYT ds over S sine alpha plus cosine alpha. And this is for inclined stirrups. Okay. So that is the contribution. So the total shear resistance Vn that equal to Vc plus Vs. All right, Vn equal to Vc plus Vs, and phi Vn, that is the design strength, should equal to phi Vc plus Vs. Okay, and the whole thing has to be greater than or equal to the applied shear force, Vu. Okay, applied shear force, Vu. All right, so as you can see that this is pretty much everything you needed for shear design, pretty much everything you needed for design. You can find this in the ACI 318-19. Okay, so this is all shear design equation. All right, so you can see that this is not so bad, right? This is not so bad, but when we look at the things, right, we like to see that what is the minimum amount of reinforcement needed for shear design, minimum amount of reinforcement needed for shear design, right? So today, which is lecture 12, I think, let me check, lecture 12, and we're going to continue to talk about design portion. Since this is kind of closely related to the previous lecture, I'm just going to write down along with it, but in a Canvas, I'll separate the notes and upload them separately, okay? So now today we're going to talk about lecture 12. Shear design, okay? Lecture 12, shear design. So you were asking, Bob, were you talking about shear design before in lecture 11? Well, those are mechanism, right? Those are mechanism. Those are analysis. Those are not design, right? So today we're going to talk about the shear design process, All right, so now here, from the nominal strength design mechanism, the shear resistance VBN has to be equal to phi, separate them VC plus VS. And this whole thing has to be greater than or equal to VU. Okay, so that is our design criterion, right? But the point that I'm trying to make is that if such criterion is satisfied, that means if phi VC is greater than equal to VU, does that mean we don't need any stirrups? No stirrups are needed, right? So if my design has exceed the requirement, does that mean I'm fine? Do I need any stirrups or I don't? Okay, in this case, ACI 318 says no. Okay, and mind you that this is actually ACI 318 and at a section is red here, so you can see that this is a section of ACI 9.6.9.1.3. ACI dictates that minimum reinforcement is needed. Okay, what does it mean? It means that no matter how safe you think you are, okay, you need to have stirrups. You need to have stirrups. That means that even if the concrete itself already exceeds the requirement, you still need to put some steel in it. All right, and that specifically in the ACI 9.3.3. Okay, in the ACI 9.3.3, you can see that AV minimum amount of reinforcement equal to 0.75 square root of F prime C and multiply BWS over FYT. And this whole thing has to be greater than or equal to 50 times BWS FYT. Okay, and now this, ladies and gentlemen, is the minimum reinforcement requirement. Okay, minimum shear reinforcement requirement. Okay, so minimum shear reinforcement requirement. Okay, but this also does not mean you just check your reinforcement against with this. Okay, why? Because in the design process, it is hard to evaluate AV min in design process. Why, Bob? I mean, it's just an equation, right? You're just plugging and get everything, right? You have the, stirrup, say number 3, right? Say number 3 here, for example, EG, and this is AV min equal to, like say, 2 legs, and each leg 0.11, so this is 0.22 inches squared. I have a spacing, say 6 inches, right? So you just do the calculation, right? You find out whether AV min satisfy this requirement or not, right? But oftentimes you have 2 parameters to manipulate. One parameter is the diameter of the stirrups, and the other parameter is the spacing. So to manipulate 2, it's not such a simple thing, isn't it? You cannot just manipulate 2 in such a fashion, right? So what you really do is the other hand, right? In reality, okay, oftentimes we're given the stirrups size, okay? we're given a number of stairs or size, right? And we are responsible to determine the spacing. Okay, we are responsible to determine the spacing for the stairs. Okay, so that means the design process, right? So let me put it this way. So design process goes this way. Design process follows this way. Okay, design process follows this way. VU has to be smaller or greater than phi-VN, and has to be smaller than or greater to smaller than or equal to phi-VC plus phi-VS. Okay, and that means VS shear contribution has to be greater than or equal to VU over phi minus VC. So for the vertical stairs, right, since VS equal to AV FYT and multiply spacing DS over S. So as required, spacing, right, has to be smaller than or equal to AV FYT DS over VU divided by phi minus VC. Okay, so that, ladies and gentlemen, is the spacing design. Okay, spacing design. So we call it spacing design, right? So spacing design means that oftentimes we're given the stirrup size, and design for spacing, design for S. Spacing. Got it? Okay. So if this is the case, right? If this is the case, what if you want to ensure AV mean, like I said, is satisfied, is greater than or equal to, just take this one out, greater than or equal to 50 times BWS over FYT. What if this is the case, right? So this is equivalent to a spacing has to be smaller than AV FYT divided by 50 BW. Okay, that is the requirement. That is the requirement. If you invertly trying to find out the spacing for the minimum reinforcement, okay, minimum reinforcement requirement. Okay, so that is the minimum spacing, or we call it actually the max spacing because that's the maximum spacing you're allowed to have it, right? So that is the equivalence. That is equivalence. Now, folks, I want you to remember these equations. I hope you can remember these equations because in the next exam, you'll see a lot of these equations, right? In the next exam, you see a lot of these equations. Okay. All right. So that is what we're going to do, right? So that is the shear design part of it. But not only that, right? There's other considerations that in addition, like we just mentioned, right? We need at least one stirrups, at least one stirrup. Oh, one stirrups, at least one stirrup needs to be present. Sorry, spring break ruined my handwriting, right? Needs to be present in a shear crack zone, right? In the shear cracking zone. That means along the diagonal, 45-degree diagonal line, okay? Along the shear cracking zone. What does it mean? It means that the required spacing of shear also has to be smaller than ds over 2, right? The depth over 2, right? As a matter of fact, the maximum spacing by ACI says has to be lesser of two numbers, right? One is ds over 2, and the other is 24 inches. And you can find this in the ACI code 9.7.6.2.2. Okay, so that, ladies and gentlemen, is the spacing requirement. Okay, all right. And in addition to this, right, there's another requirement that says actually when VS is the shear resistance from the stirrups is greater than 4 squared F prime C. Actually, there's a lambda here, 4 lambda squared F prime C BWS. And then S max has to be lesser of half the spacing in the previous one. So ds over 4, and this is 12 inches. Okay, and this is an ACI 9.7.6.2.3. 2, still 2. Okay. All right, so that is where we're at for the shear spacing. Okay, all right. So now you take a look at this, right? So this tells us, right, I have 4 criterion just to design for shear. 4 criterion just to design for shear, right? Number 1 is that has to come from contribution of stirrups, right, for shear. And then number 2 is the minimum requirement, so AV min, right? And number 3 is a spacing requirement as max. And number 4 is also a spacing requirement max. Okay, but there are so many, 4 of them, right? So how do I design them? How do I utilize these 4 equations? It's a nightmare, right? So now we actually come up with a table, tabulated table for this design, right? So next, let's introduce shear design table, okay? Shear design table, we should use a division line there. So shear design flowchart, or you can call it shear design table, okay? Shear design table. All right, so what are this table? So these are the table. First, okay, first, you calculate the applied shear force of VU. It has to ensure that this number is smaller than, or equal to phi Vn, and that is equal to phi Vc plus phi Vs. So Vs has to be greater than or equal to Vu over phi minus Vc. Got the shear resistance first, right? Got the shear resistance first. And after you have the shear resistance, and you say the required spacing has to be smaller than or equal to AVFYT ds over Vu divided by phi minus Vc. Okay, so that is a required spacing. And now, in addition to that, there are several other spacings. So S max, when the shear stirrups resistance is smaller than 4 lambda square root of F prime C BWD. Okay, when that happens, right? So you need to have spacing max. Maximum spacing of the stirrups is the least of 4 items. Okay, what are the 4 items? ds over 2, and then 24 inches. And these two come from the equation in ACI, from ACI 9.7.6.2.2. All right, and then you also have the other two, which is AVFYT divided by 0.75 square root of prime C BWD, and also AVFYT 50. Remember the minimum reinforcement BW. Okay, 50 BW. And now this is in the ACI, excuse me, 9.6.3.3, and this is so-called AV min requirement, minimum shear reinforcement requirement. Okay, and this is so-called to ensure 1 stirrups in the crack spacing ds. Okay, so that is the third criterion, and know that this is only happens when shear resistance is smaller than 4 lambda square root F prime C BW ds. All right, but now number 4, right? Number 4, S max is halved from 3 when Vs is greater than 4 lambda square root F prime C BWD. Okay, and square root of 4W BWD. Okay, all right, and know that, right? Sorry, I forgot one thing. Know that there's also upper bound, and this is when Vs greater than 4 but smaller than 8 ds. Smaller than 8. Okay, and pretty much 8 is the maximum shear you can ever reach. That is the maximum contribution you can see from the stirrups. All right, and when this happens, the maximum spacing between stirrups as max will be least of half the spacing. Remember, half the spacing. So what do you mean half spacing, Bob? Means that d over 4 and 12 inches. And these two come from 9.7.6.2.1. I'm sorry, 0.2.2, and this also carries, that is the minimum reinforcement area requirement AVFYT divided by 0.75 square root F prime C BW and AVFYT divided by a 50 BW. So this two is the AV min requirement. Okay. All right. So that is another maximum spacing, right? So 5 have another one, right? So for stirrups, that the yield strength is less than 60 KSI. For the stirrups, the yield strength is less than 60 KSI, okay? What you do, if less than that, right? If less than that, you use whatever it is, right? So FYT equal to FYT, but remains, right? But for FYT is greater than 60 KSI, right? For example, e.g. FYT equal to 75 KSI, right? Sometimes happens, right? Have a high strength stirrups, usually not so often, but what you do is you use FYT is 60 KSI. Means that the maximum shear yield strength for the shear stirrups has to be kept, Okay, and this you can find out from ACI 20.2.2.4. All right, and last but not least, your shear resistance from the stirrups S max, VS max, right, has to be kept. That means cannot exceed 8 times F prime C PWDS. Okay, and this you can find ACI in 22.5.1.2. Okay, all right, now you see that, right? This is pretty much the process. Okay, you start from checking the applied shear against the contribution from the concrete PVC, and then find out the shear resistance for the stirrups VS. And once you find the shear resistance for stirrups, basically this is VS, right? And you can use that, plug in this equation to find the required spacing. All right. And after you have the required spacing, you need to check if your VS is smaller than 4 times square root F prime CPWD, you do another spacing requirement check to make sure that these are spacing and your calculated spacing as required has to be smaller than maximum spacing. Okay. And then if your shear resistance fall in the second category, you need actually to say that, look, this is falling this category, so has to be smaller than these sets of maximum spacing. And make sure your stirrups is within 60 KSI if yield strength, and also make sure that your total shear resistance from the stirrups is bounded below A square root F prime C BWDS. Okay. And when I say bounded, meaning that if this happen, right? So if you find out your shear stirrups or shear resistance from stirrups has exceeded this number, very rare chance you see that, but if you see this, right, what do? You actually have to tell the engineer, or you do it yourself, has to say that increase the section size. So, Bob, what do you mean increase section size? That means increase your BW or your depths of the beam. Okay. All right. So this is pretty much you need to do for shear design. Pretty much you need to do for shear design. Okay. So at here, I want to pause for a second. Any questions? Any questions for shear? Anything, folks? Anyone? Questions? Anything so far? We okay? All right. Okay. Well, I know it's the first day back from spring break. I'm still doing this online, so you might want to hold up your question for a little bit. And Wednesday, we can talk about it as well, okay? But now with this, I think we can see some examples, right? We can see some examples. So today, let's continue to show some examples on the shear design. So example on shear design, okay? Example on shear design. Okay, shear design. So given the beam like this, a rectangular, nice rectangular sections, and have a width of the beam that equal to 12 inch. Okay, height of the beam that is equal to a 24 inch. Okay, and have some bars at the bottom row, bottom right here, bars right here. And these bars are for number 8. And I have a depth of the section of 21.5 inch. That means that I have a concrete cover of 2.5 inch. Okay, So now we're going to ask you to design for the section. That means design for the stirrups, right? So let me just label the stirrups. You can see that. So I'm asking you to design for the stirrups. Okay. Normally, when you see this, you will have compressive reinforcement. That means you have some compressive reinforcement here, compressive reinforcement here. Okay. And the question is that, right? Question is that when you have a simply supported beam with this section, that means my beam is simply supported like that. The beam is simply supported like that, okay? And then I have a shear diagram, right? I have a distributed load, which is a triangle shear diagram like this, okay? Shear diagram like this, triangle shear diagram like this, okay? And that tells me that I have a maximum shear right here. I have a maximum shear right here, okay? But when you design it, you take a spacing of ds away from that, and this, okay, take a spacing away from that, and this to maximum point is the real VU, okay, is the real VU. And don't ask me why, and I'll explain to you in the next lecture, but this is max VU. So how does that translate in actual image, right? How does this translate? Oops. How does this translate in the actual image, right? So in the actual image, it actually translates like this. I have a beam like this, and this is unsupported, and I have a pad right here. And usually you see that is like a rocker, and then have a joint, and then supported on neoprene pads. And this whole thing sits on a column like so. And then the center line of the column sits right here. That is the center line of the column. And then the spacing is actually ds away from the edge of it, right? Ds away from the edge of it. So you actually have a critical section, right? So right here, ds away, right? So ds away from the critical section, okay? So ds right here. Okay, well, actually, not so accurate, right? Sorry, folks. So it has to be from the center line right here, ds. Okay, ds. So that crack is my 45-degree line here. That's my 45-degree here. Okay, and this is so-called critical section. AA is critical section. Okay, so now VU is sitting right here at this critical section. Okay, all right. So basically, we're going to ask you to design stirrups, and that include number of stirrups and also spacing for the stirrups. Given that applied shear VU is at a critical section ds away from the support. Okay, so the question is that design for section on the left. Okay, oh, oops, on the left, right? And I want you to design for the stirrup size of stirrups, and the spacing of the stirrups. Okay. And given the shear force VU equal to A, 12 kips, B, 24 kips, C, 54 kips, D, 77 kips, and E, 128 kips. Okay. We want you to design for this, right? It's a gradually increased fashion, right? So it's increasing, okay? And given the design parameters F prime C equal to 4 KSI, normal concrete, and yield strength for the stirrups, and note that's YT, okay? Equal to 60 KSI. All right, and just to ensure that this is normal weight concrete, so lambda equal to 1.0, and this is normal weight concrete, okay? Normal weight concrete. All right, and to design for this, let's dive in, right? Let's dive in. So first case, I have a 12 kips of shear. And mind you that this is VU, okay? This is VU. All right, so given that we know VVN, design shear has to be greater than or equal to VU. So that means VC is the concrete resistance, right, for the shear. So that is equal to 2 lambda square root of F prime C BWD. So equal to 2 times 1.0 times square root of 4,000 psi, 4,000 psi, okay, and multiply 12-inch, which is the width of the section, and multiply depth of it, right? Depth is 21.5 inch, okay? And so for this, VC, you do the calculation and you find out that it is about 32.6 kips. Save it the hustle, just did myself. And then with that, I say phi VC, which is the reduced shear resistance of the concrete, right? And you know that the reduction factor phi for shear is 0.75, okay? And that is 0.75 multiplied by 32.6 kips, 32.6 kips, and that gave you 24.5 kips, okay, 24.5 kips. Immediately, you can tell this is actually bigger than the applied shear, which is VU over, VU of 12 kips. Okay, this is actually larger than the design shear, which is VU equal to 12 kips. Okay, all right. So at this moment, okay, I started to realize, okay, so if this is the case, matter of fact, my phi VC divided by 2, and ladies and gentlemen, I need you to focus here, okay? Phi VC divided by 2 equal to 24.5 kips divided by 2, and that is still larger. So it's 12.25, right? Still larger than the applied shear, which is 12 kips. Okay, and what does that mean, right? It means that if you have this criteria satisfied, you have this criteria. If you have this criteria satisfied, okay, half VVC is bigger than the applied shear VU. If you have this criteria satisfied, you're saying that, okay, I just need to provide no additional stirrups needed. Additional, okay, but still need to provide it and be minimum is required. Minimum stirrups is required. Okay. All right. So what is this a minimum shear resistance, right? So you remember AV min, right, has to be greater than or equal to actually two things, right? Two things by the two equations right here. I may have forgotten one from the previous one, but these two, right? These two, right? So one is 0.75 square root of prime C BWD. Okay, and forgot something here. BWDS AVFYT. So this is divided by FYT. Okay, and the other one I think is my bad memory fails me today. 50 BW divided by FYT. Okay, so just have to check these, right? And then provide enough stirrups. Provide enough stirrups. Okay, so this is one bottom line for the A case, right? Just provide some stirrups and you'll be fine. Okay, and you can check yourself, but pretty much any stirrups will suffice, except number 3, and then you go with the spacing DS, that will work. But we don't really worry about it. Okay, matter of fact, if you just put any reinforcement that satisfies these requirements, you're fine. Okay. So move on to the next one, B equal to VU at 24 kips. It's a little bit higher force, right? 24 kips. What happens? In this case, what happens, the phi VC is the concrete contribution, right? That keeps the same, remains, right? Still 24.5 kips. And that value is still bigger than the 24 kips, which is the shear that applied, right? Shear applied. So in this case, half of VVC is 12.24 kips, and this number is smaller than VU now. In problem A, it is still bigger, right? But in problem 2, we increased the VU, so this is now smaller than VU now. Okay, so when you have this case, no need to calculate, so no need to compute for VS, okay? Use maximum spacing instead. Okay, use maximum spacing instead. So which maximum spacing I need to use, right? Which one? So you check VS, right? That has to be smaller than 4 times square root of F prime C BWD. And you can check it, and this is indeed the case, right? So when that happens, I say maximum spacing has to be least of the 4 numbers from the previous table, right? So first d over 2, at least have half of the spacing satisfied. d over 2 is a 21.5 inch divided by 2, and that gives me a 10.75 inch of spacing, or 24 inch, or AVFYT divided by 0.75 square root F prime C BW, okay, or AVFYT divided by 50 BW. So this number right here is 0.22 inch squared. And why 0.22, Bob? So you notice that I already assumed number 3 stirrups. So when you are not given the stirrup size, it always go with number 3 first, okay? Always go with number 3 first. Okay, so now 0.22 inch squared multiply a 60 60 KSI of yield strength divided by a 0.75 multiply square root of 4,000 PSI of concrete, and BW is 12 inches. So you got this number to be at a 23.2 inches. Okay, and you do the same calculation for the lower one. So this is 0.22 inch squared and multiply FYT 60 KSI and divided by 50 and BW again 12 inch. You end up with a 22 inch of spacing. So this is for these two, right? The top bottom here, 10.75, 24 inches, right? So out of these 4, 1, 2, 3, 4, and you pick the smallest number, least of, right? So this number 10.75 governs, right? So this one governs. All right, so now you conclude, you say S spacing has to be smaller than the S max equal to 10.75 inches. Means that this is for number 3 stirrups, okay? This is for number 3 stirrups because I use that in the assumption, right? So that means if I say I provide S, okay, S of 10 inches, smaller than this, right? Let's go with a whole thumb number, right? 10 inches at a number 3 stirrups, then I satisfy the design need. Okay, I satisfy the design need. All right. Now you look at this, right? This is for problem B, right? I provide 10 inch at number 3 stirrups. Okay, and I circle back to look at the problem A. The problem A says I need to have some minimum reinforcement. So pretty much everything you can throw in that satisfy this minimum reinforcement will work. And I would just say that how about I just take this number for both A and B, right? Because they also works. You say, Bob, why are you so lazy? Well, the reason is I think of it, right? In the shear diagram, right? Which we'll talk about later today. In the shear diagram, VU start from a higher end of the spectrum, right? As you're approaching from the middle of the beam, VU start to decline, VU start to decrease. Is that right? So you think of it, right? It must come upon a certain area, right? Certain area where you have 12 kips of shear right here, right? 12 kips lying right here. And you also have 24 kips of region on the outside, right? And you will be facing a choice that whether I provide one spacing in this region, and this is S1, and another spacing in this region, S2, or I can just provide one uniform or one spacing for both regions. Now, the answer is yes. Why not just give one spacing for both regions? Because that way you save the effort of having different design in construction. You make the construction easier. Okay. All right. So now you see this is how we're going to design. Okay. Now my time's up today, and I'd like to quickly sum up because I don't want to get into the second one and third one could not finish. So you take a quick look at what we have done, right? So we start increase the applied shear. As applied shear increases, right? Our stirrups requirement increases as well. Beginning, barely anything will work, right? Just throwing in some steel should satisfy the requirement. Then afterwards, you start to have some requirements. And then you can use a higher requirement to cover the lower end. The cost is that you add more materials to it, but the benefit is that you made the construction easier. Okay, all right. This is a very good place to pause. I'm just gonna pause here. And if you have any question, please leave behind and we can talk about it. If not, I'll see you in person Wednesday morning. Okay, I see you in person Wednesday morning. Thank you, and see you then. Bye.